What's up, CoderByte? Welcome back to another data structures and algorithms video. I'm Elizabeth, and today we're going to be continuing the Back to Basics series, where I'm kind of just taking a problem and trying to solve it just live on the fly for you guys. Today's problem is I don't know, it's one I really like. I think I'm going to approach it. I can approach it in two different ways, a recursive way and a dynamic programming kind of way. So those are two concepts I've personally struggled with. I think probably everyone has. So I hope that it's useful to kind of walk through it and follow along with my thought process as I solve it. And with that, let's get into this week's problem. Write a function to return the number of possible paths from one corner of a grid to its opposite corner. Okay, so let's look at an example, what we possibly mean by grid and what we mean by possible paths, etc., one corner to another. So here we have kind of a 2x2, small little grid. And I think the thing to be kind of cognizant of is, what do we mean by corners? What do we mean by opposite corners? What do we mean by path? So I think for this example, we'll probably start at 0, 0, which I would say is the top left corner of this grid. And we're trying to see how many paths there are to the opposite corner. So that's going to be this one right here, which would be, if this was indexed in an array, this would be, 2, 2 or 1, 1, right? Because we start at index 0. So let's see what the possible paths would be in this scenario. So here we have 6 possible paths, which are all the ways that we could possibly get from this 0, 0 point to this 2, 2 point, right? And we can see that what we kind of determine as a unique path is the corners, right? It's not this whole square. It's actually this corner to this corner is a piece of a path, and then this corner to this corner is a piece of a path, etc. So even though this is a grid that you might say is a 2x2 kind of grid, what we're actually looking at is a 3x3 kind of grid, because it's three corners by 3 corners, right? We have this point, which is 0, 0, this point, which might be 0, 1, and this point, which might be 0, 2, and then let's say this point, which is 1, 0, and this one, which is 1, 1, and this one, which is 1, 2, etc. So that's number one off the bat. Our grid is actually going to be of the corners rather than of the squares, if that makes sense. I think that's pretty self-explanatory. So if you got this exact grid, your function should return 6, right? So let's just make sure that that's correct. Yes, so 6 possible paths. So yeah, let's start coding this up. Okay, so like we've been doing for all of these back to basics videos, I'm going to be using Python for this. So I just have my PyCharm IDE open up here with a file called paths.py. So like usual with any Python code, we can set up our kind of dunder name thing to run the main function. So if dunder name equals dunder main, right, we're going to execute the function. So let's say, I think I'm going to try and do this recursively first. I wonder if that's easier than the dynamic programming way, but leave it in the comments below which you think is easier or which you think is harder, because I think they're kind of both a little bit tricky. So let's say we're going to call our function maybe like number of paths recursive. That's a good name. Yeah, let's do that. We're probably going to print that, right? And I don't know what that's going to take yet, so let's not fill that out yet, but we can just define our function here and say pass, so we don't have any of those squiggles, because gotta hate those squiggles. Okay, so I think, how are we going to approach this? I think what we're probably going to do is we're probably going to have this take how big is the grid, right? And that way we can have a function that kind of creates the grid however we want it to look. And we can just ask our users like, hey, like, you're going to give us the kind of bounds of the grid, how big we want it to be, and we'll tell you how many paths there are. So let's say this is going to take, right, this is going to take the grid size. And so let's put in 3 because that's the example that we have, and it's kind of obviously as the grid grows, the paths grow very quickly. So I think 3 is a really nice middle ground between, like, there are a bunch of different paths, 6, but there aren't like a million paths. So let's try that for starters. Okay, so the first thing we want to do here is we want to like create a grid, right? So we want to, basically define, not define really, but just like initialize, that's the word I'm looking for. Initialize, nope, initialize. Yeah, there we go. Initialize the grid here, right? So I think for right now, we can just have a, basically an array of arrays of zeros. I think that should work here. So I think I'm just going to use, I forget what it's called in Python. But basically we're going to like loop through the range of the grid size, and we're just going to fill in a bunch of zeros. So I think we want an array of arrays, right? So I think what we're going to want to do is we're going to want to fill in zeros, right? For I in range grid size. And then we want to do that. We want to have that many arrays of zeros for j in range grid size. So that will be our, array of zeros and then an array of arrays of zeros. So that's kind of how we can do that. So let's just see what that even looks like, just to make sure that everyone is on the same page here. And let's run this. Okay, so you can see here that we have our arrays. We have 3 arrays of zeros, right? And each array has 3 zeros. So that's kind of our, our grid of corners. Remember, we're not thinking about the squares here. We're thinking about the actual corners from, point to point on this kind of, we're thinking of the lines of the grid rather than the empty spaces inside the lines. I don't know if that makes any sense. I hope you guys understand what I'm saying. Okay, so we have our grid, right? And now we want to kind of create our function, which is going to start to traverse this grid and look for all of the possible paths. So I think what we're going to want to do here is we're going to want to do some sort of like, we're going to want to keep track of the paths as we find them and essentially set off recursive calls for every, going to the every right neighbor and every down neighbor, right? We're going to keep moving right and down until either we reach that corner we're looking for, which is the bottom rightmost corner, or we reach somehow the bounds of the graph to stay within the bounds of the graph. And I think because we want to kind of track each path, we want to know all of the paths. I think what I'm going to do is this is going to be kind of our main function, our parent function, which holds all of the paths that we found. And then we're going to create a different function that we're going to call within this one, which is going to be the function that actually calls itself recursively for each path individually. So this is going to be the kind of like collector of the paths, and then we're going to have a function that actually finds a path. So let's set that up, I guess, above here. So this is going to be our find paths, or maybe really find path I kind of like better because we're just finding the one path. And this is going to be a function, and let's just put a path in there for now. So we know definitely that this is going to take the grid, right? So let's put that in right now. And we can kind of put this in here as well. We don't have to print that anymore. So we basically are going to want to call find path on the grid, right? And then what we're going to want to do is we're going to want to collect all of the paths in some variable here. So let's say paths equal an array, and we're probably going to want to pass that in because we're going to want to be pushing all of the individual paths to this paths array that's keeping track of all of the possible paths. So let's do that right here. These are all of the possible paths, right? And we can add that in here. And then I think the other thing we're going to want to do is we're going to want to track the current path, right? So we're going to want to somehow initialize some current path. And I think here, I'm going to put that before this one. So I'm going to say current path, and I'm going to default that to an array, just in case, we're initializing it to start. And I think that probably it's going to be upset because maybe I'm going to do that at the end, because then we can use those default arguments nicely. So that should just work, right? Okay, so at first when we call it, there's no current path yet, so we're just going to initialize an array. And for each recursive call, we're going to be basically appending every next corner to the current path. And then when we reach the bounds of the array, the bounds of the grid, we can stop those recursive calls, push that whole thing to the global paths list, and then kind of start anew. So that's kind of what I'm thinking right now. Okay, so we have our find path, we have our paths array. I think the other thing we're going to want to do is we're going to want to keep track of where we are in the grid at any given point, right? So that's going to take, let's just do like I and J. And that's basically going to symbolize or represent where are we in the grid at this very moment in time. So I think when we start, we will want to start right at that top leftmost. So that will be 0, 0. So we'll start with 0, 0 there. And let's kind of see what we get with that. I think that is really going to be more or less it for this. And I think what we'll probably do at the end of this is just return the length of that paths array, right? So I think this is more or less what this function is going to look like. And the meat of this algorithm is going to actually be in the find path function. So let's start writing that. Okay, so this is we know we're going to be calling this recursively, right? So we obviously, the number one most important thing in any recursive function is kind of defining our base cases. So what are our base cases? I think our base cases here are that we've reached the end of the path, right? Like we've actually reached that bottom rightmost corner. So first, I think we can kind of define like what is that rightmost corner. So that's going to be kind of our bounds of this grid, if you will. So let's say like, the bounds of this grid are M and N. And we're going to define that as the length of the grid, right? And the length of the grid at 0. So that's going to be the length of the grid is how many arrays are there, kind of going from top to bottom. And then the length of the grid at 0 is going to be from left to right, how many zeros per row. So that the first one is how many rows do we have, and the second one is how many columns do we have in our grid. So now we have two variables, M and N, and that's going to kind of help us kind of when we reach those bounds in our logic, like, no, we're done, we found it. Okay, so let's see. So in this case, what we want to do is we want to basically, right, if we've reached the bottom rightmost corner, what do we want to do? We want to take current path and add to paths, right? Add to all of the paths, because that means we have a path that we've been tracking, and that's great. Save it. And then we want to return, right? We want to just like, we're done. This is our base case. So what is that going to look like here? So I think what we'll do is we will say, we want to check, right? If I and J represent where we are in the grid, we want to check, is I and J equal to M or N, right? M and N. And if that's going to be M and N minus 1, because arrays start at index 0, right? So the length is going to be the actual index of that corner will be the length minus 1. So that's pretty simple, right? So if I is equal to m minus 1 and j is equal to n minus 1, right? Because that's our kind of coordinates here. We want to say paths.append the current path, right? And return. And I think that's really all we have to do here. So because we don't have to return the path because we're keeping track of it in this kind of like manager function. Okay, so what do we want to do outside of that, right? So that's our base case. So what do we want to do? We want to be traversing, right? We're traversing this graph. So we want to traverse to the right, right? Traverse to the right, and we want to traverse down. We always want to check, like, can we go right? Can we go down? So what we want to do is, what does it mean to be able to traverse to the right or traverse down? Essentially, is there a neighbor to my right, or am I at the end of my road here? So how can we check that? We can basically check, so we need to first make sure, right, that I think I will always be greater than 0 because of how we're starting this, but we can add that in here just in case. We want to make sure that I is greater than 0, greater than or equal to 0, and it's also less than m, right? And we also then want to check, so actually we don't want to check I, we want to check I plus 1, right? Because we want to check is the neighbor, can we go any further, or is this the end of my line here? So that's going to look like this, right? If 0 is less than or equal to 1, no, wait, if I is greater than or equal to 0 and also less than m, right? And actually to move to the right, that's going to be j. So we're not even incrementing I yet. So we're just checking, is I in the bounds, right? So if I is in the bounds, and now this is where we're going to try and move to the right, if j is greater than or equal to 0, and, or excuse me, j plus 1 is greater than or equal to 0, and also less than n, which is because we want to check, can we move to the right? Is it less than the bounds? So that's why we do that like double check where we check, is it in the bounds past 0, and is it in the bounds past that n? And if that is the case, we want to call this function recursively with j plus 1 as the new j, right? So we can say find path, and then we want to pass it the same grid and the current path, but not in that spot. We want to pass it the paths, right? And then we want to pass it I, because we're not incrementing that. And then we want to pass it j plus 1, that's going to look to our right. And then we want to pass it that current path, right? So at this stage, current path is going to be an empty array. So we're going to have to figure out like how do we add to that current paths, right? Like, and when do we add to that current paths? Okay, so that is the move to the right. Actually, we kind of have to think about that now. We can't wait for that, right? We can't, I think what we want to do is before we traverse, we want to add the current node, or excuse me, the current corner. And just for the record, this is a graphs problem underneath, right? Like we're traversing a graph essentially, and these corners are just nodes in the graph. So that's something to keep in mind here. So I think here what we'll want to do is, right, we want to take that current path and we want to append to it, right, wherever we are at this given point. So here at this stage, we are at the grid at I, at j, right? So that is our current path. Okay, so far so good. Here we'll have our current path, which is going to grow as we traverse. And then when we finally hit our base case, we're going to have a current path that we've been collecting this whole time, and we're going to add that to the paths, right? Okay, so except if we want to add the last node to our current path when we reached our base case, right, we're never going to make it this far. So I think we're going to have to do this also here, right? We want to, when we get to this stage, when we're at that end, we were going to want to find that last corner piece. We want to still add it to the path. So let's do that right now, because I see that that will probably be something that we need. So what we want to do is we want to add to it, right? We want to add to it the grid at I at J. So it's basically just, it's the same thing as what we're doing here, but we're not going to reach that because we're in this base case. Okay, so now we've traversed to the right. Now let's take care of traversing down, right? So that's going to be similar, except we're going to do the +1 to I, right? So this is going to be a very, very similar, looking thing, right? So we're going to have a 0 just to make sure we're still in the bounds of, the left side of the grid. So if 0 is less than or equal to I plus 1, right, which is less than M, and 0 is less than or equal to, and then this is going to be J, which we're leaving without the +1, right? So that still has to be less than N, right? What do we want to do? We want to do the same thing, right? So we're going to say find the path, the grid, the paths, I plus 1, J, and then the current path, right? And I think that that's it, right? We're either going right or left into, right or down until we can't anymore. We've reached the bounds, or we've reached, this stage, right? We've reached that corner case. And then the current path, what we want to do after all of that, right, is we want to backtrack. We want to remove the current, whatever that cell is, from the path, so that as we traverse, we kind of, we only maintain the actual path and not all of the nodes that we're possibly visiting in this function. So I think this will be better explained with a debugger. Again, I love the debugger. I use it all the time, and I think it's very useful to kind of visualize what this means and kind of why are we backtracking? What are we backtracking? So we'll look at that in a second when we run this. So I think we can just take that whatever the latest node is that we put on that path, just pop it off, right? And this is basically, it's like a slightly modified traversal of a graph, right? We're kind of we're recursively traversing, just like when we learned in our graphs video how to recursively traverse a graph. So I think that might just work. So let's see what we have here. So we have find the path, right? We're going to call it, and we're going to return the length of the paths, and then let's just print out what those paths look like. So I have a feeling already, because what we're doing is we're making our grid full of just zeros, right? Our whole grid is just a grid of zeros by zeros. And what we're adding to our current path, we're keeping track of our path as we go down, as we traverse. But what we're actually appending to it is the value at that kind of node in the grid. And all of our values are 0. So all of the paths are going to look the same. So we can change that by not making them zeros. So let's do that. Why don't we do that, right? So I think if we just take out, I think if I just do I for I, and that should, yeah, let's print out what the grid looks like as well. Let's label it. And this is paths. And then let's see what we get when we run this. Okay, so first of all, yes, now we have this grid of 0, 1, 2. Oh, so we still have duplicates, because now it's just right? It's just like looping through each of these. Um, it just does the range and then it does that for every single thing, right? So let's actually, how can we do this? I might just cheat here and just make a small grid. Oh, I don't know how I just did that. So I'm gonna say grid is equal to 0. Well, here, right? Okay, so now we have kind of unique nodes. Yeah, let's see what we get now. Okay, so now we have all of these paths are actually different, right? And we are getting 6. So that's the 6 paths that we could possibly go down. So we can go from 0 to 1, and then from 1 to 2, and then 2 to 5, and then 5 to 8. And this is probably not useful at all without looking at at kind of like the diagram. So actually, let me just pull that up really quick. Okay, so let's try and like look at, these numbers and make sense of them here. So if this is right, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So if this path is 0 to 1, 1 to 2, and then 2 to 5, so that is there, right? And then 5 to 8, which is here. So that's exactly, it's this first one, right? Okay, so then let's look at this second one. 0 to 1, 1 to 4, which is this, it's going to probably be this one. 4 to 5, and then 5 to 8. And then let's look at one more, 0 to 1, and then 1 to 4, and then 4 to 7, and then 7 to 8. So you can kind of see how it's, keeping track of the path. And then we're just taking the length of the paths array. So let's get rid of that. And why don't we add some debugger breakpoints and kind of do this through the debugger so we can see all of the recursive calls, the branches that it creates, and kind of how we're backtracking here and why we're backtracking here. I'm going to just add a breakpoint here, here, here. When in doubt, add a breakpoint, right? Okay, and let's run this with the debugger. Okay, so here we are in our debugger. So far we have our current path, which has nothing in it, right? Because we're just getting started. Here's our grid. We're at 0, 0. The bounds are 3, 3, and there's nothing yet in our paths. So let's walk through this. So the first thing we do is we add where we are to current path, right? So current path is now going to get whatever's at grid ij, which is going to be 1, right? I believe that the grid, yeah. Oh no, the grid starts at 0, so it's going to be 0. Okay, so we have our current path, right, now has a 0 in it, and we are traversing to the right. So I is greater than or equal to 0, and it is less than m. And j plus 1, which is, right, j is 0, so j plus 1 is 1, is greater than or equal to 0 and less than n. So we're going to fall into here, and let's see what happens. So we're going to set off a new branch of recursion, and we are going to increment j to kind of signify that we're traversing to the right, and continue to pass in that current path, which now has a 0 in it, right? Okay, so here we are, we're back at the top of the function. Our current path has a 0 in it. I is 0, j is 1. So let's walk through. It's not there yet, right? We're not at the bounds. So we're going to append where we now are, which is going to be 0, 1, right? So that's going to be 1. And so now current path has a 1 in it, right? Because we're traversing to the right. So can we still traverse to the right? You bet we can. So we're going to set off another branch of recursion now, and we're back at the top of the function, etc. So let's just, continue walking through this. We are, right, so I is 0, j is 2, right? So we're still not there yet, right? Because I is still all the way to, I is still 0, so we're still on the top row. But j is at its bounds, right? So j plus 1, which is going to be 3, is not less than or equal to n, right? So what is going to happen here? So it's not going to fall back in there, but it's going to now traverse down because we've already reached the end of traversing right. Okay, so we continue to traverse, right? And we now start a new branch. Okay, so now we have our current path, right? Because we've gone from 0 to 1 and then 1 to 2. And we're now going to we're going to keep traversing down, right? So we're not going to fall in there. We're going to pass in 4 because that's where we are, right? Or excuse me, 5. And we still can't traverse to the right from there, right? So we're going to continue to traverse down. So we're going to have a new branch of recursion, and we are going to increment j. We're back at the top. Now we've gone from 0 to 1, 1 to 2, and then 2 to 5, right? So we are going to continue down. That's still not true yet. Oh, it is true because now we're checking, right? Because we are, the bounds are -1 because of that length and index thing. So we are at the end. So what is at grid I and j? It's going to be that rightmost corner, right? Okay, so now we can append this whole path, which is 0 to 1, 1 to 2, 2 to 5, and now we're going to append, or excuse me, 2 to 5, and now we're going 5 to 8. So we're going to append 8 and also append this whole current path to our global paths tracker, right? And we're going to return. So we're done, right? And now what we're doing is we are backtracking because now we have to kind of reset our current path back to an empty array, right? So we're backtracking up until we get back to 0, and then we're going to find all the other paths. So the backtracking is what helps us call this function for every single path in the grid, if that makes sense. And we basically, so every time we backtrack, we then continue to traverse in whatever other ways we can to find all of those other paths. Because you see, there's nowhere in this function where we're comparing, have we seen this path yet? No, because we don't have to, because we do this traversing and then backtracking. And because we backtrack, we'll never see that node again. It's always going to be a different branch. So let's just watch that happen. So now we're popping, we're going back, right? We're popping, we're going back. Okay, so now where are we? So now we're at 0 and 1, right? So what is the grid at 0, 0, 1? So 0, 1, we've gotten all the way back to the 1 corner, right? So that's the top middle corner. And now we're going to go from that top middle corner, and instead of going right, like we've already done, we're just going to go left or go down, excuse me, and we're going to, have a new path. And we don't have to traverse the whole path from 0, 0 again, because we just had to backtrack until we got to another, branch of the recursion, if that makes sense. So let's watch that kind of happen live. So now we're going to do more recursive calls. And now our current path is 0, 1, and we're going to start to create our next path, which is going to be the 0 to 1, 1 to, I think, 4, 4 to 5, and then 5 down, right? So let's watch that happen here. Okay, so here's our 4. So we've now backtracked up to the 1, and now we're trying to go down, or we did go down. And now we're at 4, we can go to the right again. So we're going to go to the right, right? And now we've added 5, right? And here's 5, we've added to it. And now 5, we can't go right, we're going to go down. So here we are going down. Call it again. Now we're going to reach our base case, right? So we append it, we return, and then we start to backtrack again. We backtrack until we get back to a spot where we can traverse a different way. So I hope that makes sense. Again, I highly suggest you code this out yourself and walk through it with a debugger like this. I think it makes it, like, all of these recursive calls, especially with backtracking, it makes it really easier to reason about as the function runs and what's actually happening. It helps me personally visualize the recursive branches. And also, I always find it so cool. I'm like, oh, wow, that is very cool that works and that it makes sense like that. So anyway, let's get on to the dynamic programming solution. Okay, so for our next solution, we're going to do it in a more dynamic programming style sort of way. And with this solution, what we're essentially doing is instead of kind of traversing a graph, that has been given to us in the function, we're going to create a graph to almost represent the graph that they're asking us to traverse. And while we traverse it, we are going to keep track of the paths that we're taking and how many other paths almost overlap with whatever path we're on. And as we reach that bottom rightmost corner, we're always going to know how many paths have been able to reach that point, because we track it as we traverse. So I don't know if that makes any sense at all. Hopefully with the code, it will make a little bit more sense. But let's get into it. We'll walk through it, and it'll all be fine, I promise. Okay, so here we have our the same file that we've been working in. I'm just going to comment that out. And let's say we're going to print the number of paths dynamic. And we're also going to, probably pass it a grid size and kind of do something similar. So let's define this function. There we go. And here we have our grid size. Okay. So essentially what we want to do is we want to kind of, like I said, initialize a graph. And at first, it's just going to be zeros because we haven't traversed it yet. We haven't had any paths so far. So we're going to do something kind of similar to what I did here. So I'm going to copy and paste this, clutch. And here we have our grid. And now we're going to actually do just the 0 for I in range grid size, right? So this is going to basically initialize that grid. And essentially, like these are going to be, we're using this grid to track our paths. So I might even rename this to paths just to be kind of like explicit about what we're doing here, because we're going to be modifying all of these zeros and we're going to be basically incrementing as we reach the different corners in the different ways that we reach them. So you'll see that in a second. Okay, so we want to do a breadth first search, right? So breadth first search, just as like a reminder, is when you have a node and you search all of its children before you search any of its children's children. So in this way, we're basically going to be starting at that top leftmost node, and we are going to traverse all of its children, so to the right and to the bottom, essentially, before we continue to traverse its neighbors to the right, neighbor to the right, etc., etc. And so to do a breadth first search, we use a queue, right? First in, first out. And we essentially just take, we take from the beginning of the queue, and we traverse whatever that means. We'll see what that means in this case. And then, we remove it from the queue as we traverse. So let's set that up. Here we have our queue, right? And then this is going to just be like a while loop. So this is going to be while there is anything in the queue, right? And I think what we want to do here is we want to initialize the queue with that 0, 0, right? The top leftmost corner. So that's just going to be, right? Let's just say like 0, 0. So that's kind of our coordinates of our first spot. So let's kind of build the bones of this traversal, if you will, and then we'll talk through like what is the dynamic programming piece of this. How are we going to track how many paths we've actually seen? Okay, so here we have our queue, right? And what we basically want to do is we want that first thing off the queue, right? So let's say the current is, I think we can do a queue.pop And if we pass 0, it will take the first thing off instead of the last thing off. And what that's going to be is now going to be, right, that tuple of the coordinates, essentially. So we can say that the current x, and this is always funny when you have arrays of arrays, that the first, if you have like a, like a paths at x, y, oh, no, that's not what I meant to do, at x, y, right? So this is, of course, which row it's in, so that's actually the y, and then this is which column it's in, which is actually the x, so it's swapped. So just remember that. It's a little confusing, but such is life. Life is kind of confusing. Okay, so we have our current y, which is going to be the current, right, at 0. That's the first, that's this is our y kind of coordinate, right? And then we have our current x, which is whatever that current is at 1, right? Okay, so now we have our kind of x and y where we are in the grid at any given point. So what we want to do is we want to basically, right, we want to check if it has children, or not children, but does it have a neighbor to its right? Does it have a neighbor to its to down, right? And we want to add those things to the queue because we want to traverse them. So let's check that. So that's going to be something like, under neighbor y, right? So this is going to be the neighbor. I'm going to make a comment here. If there is a neighbor underneath it. Okay, I don't know. So this is the under neighbor y coordinate, which is going to be what? The current y minus 1, or excuse me, plus 1. It's under, but it's plus. Everything is upside down, but I think everyone knows that. Okay, so this is the current y plus 1, right? And then let's say the right neighbor x is going to be the current x plus 1, right? So that's going to be the neighbor to its right. So this is going to be similar to kind of what we did earlier, where we just first check, is this in the bounds, right? So we need to check that if 0 is less than or equal to the under neighbor y, which is less than the grid size. So is it in the bounds, right? What we want to do is, number one, we want to check, is it already in the queue, right? So we can do that pretty simply. We can say if under neighbor y, so what are the coordinates of the under neighbor y? The under neighbor y has the same x, right? So that's going to be current x, right? So if that value, not in queue, we want to append it, right? We want to append a new tuple, and this is going to be the under neighbor y and the current x. This just adds it to the queue because we haven't seen it yet, so add it. So let's do the same thing for our right neighbor. So this is going to be if there is a neighbor to its right. And this is going to be something similar. This is going to be if 0 is less than or equal to the right neighbor x, right? Which is less than the grid size, similar, kind of idea here. What we want to do is we want to also check if the current y and then the under neighbor, no, the right neighbor x, not in queue, right? So we want to check, is this neighbor in the queue? If it isn't, we want to append, right? We want to append the current y and the right neighbor x. Okay, so this is just a regular old traversal, right? And this will work. I believe we can run it, but if we wanted to just traverse and not do anything with any of these values, this is how you do a breadth first traversal with a queue. Okay, so what do we want to be doing here though? What we essentially want to be doing is as we visit these corners, we want to keep track of, have we been here before? Are there other paths that overlap with this? And now I'm in a new path and we already have had paths that have been here. And it's not that we've already done the whole path before as a duplicate, it's that there are certain parts of the path that overlap. And if we can keep track of that with each kind of traverse, each iteration of this traversal, we can essentially, by the time we get to the bottom right node, whatever number is there is all of the paths possible, because that's going to be, right, we're going to have gotten there, and there's going to be a bunch of different ways that we've gotten there, and we've tracked all of that, and we can just return whatever value is at that kind of bottom right corner. So we can walk through this with an example in a second, but so essentially we haven't done anything yet, right? We're at 0, 0. So what we want to do is we do want to initialize that at that first spot. We can initialize it with a 1 because we're visiting it. We've added it to the queue. We've already visited it. That's our first path, right? So what we can do here is we can just set paths 0, 0 equal to 1. Okay, so now we have a 1 in that top leftmost corner. And we now have the top leftmost corner in our queue. So when we pop that off, we now have that, right? And essentially what we want to do is we want to update every time we do this every time we add something to the queue. We want to add whatever is at our current, however many paths have happened at our current node, we want to add that to our next node so that every single traversal kind of represents all of the traversals that have happened thus far. So all of the paths that have led here to date, we are now keeping track of in each node. So that's, again, pretty simple. This is just going to take, I think we can just do that right here. So we're going to do our paths so we want to set our next neighbor to be equal to whatever was at however many paths we've had at our current neighbor, we now want to add that to the next neighbor. So that's going to be the paths at the under neighbor y and the current x, right? That's the underneath neighbor. We're just going to add to that whatever is at our current, right? Our current y and current x, or our current node. And in that way, we kind of continue to build on however many paths we've had thus far. And eventually we get to that, the rightmost corner, the right bottom corner, and it will be keeping track of all of the paths thus far. So this is going to be very similar down here. So that's going to look like that, except this is going to be the current y and the right neighbor x. And then this is going to be the current y and the current x. So that's the same, right? And then what we want to do is after the traversal is done, we just want to return the paths at the grid size -1 because of that index thing, right? At grid size -1. And whatever's there is going to be the number of paths and how we've gotten there. So we'll do this in the debugger, obviously, and we'll kind of walk through how this is working and what's exactly happening here. But let's first run it and see if we get our 6 as we hope. And we do. Okay, so here's our 6. Okay, so let's walk through the debugger and see kind of what exactly is happening. So yeah, let's put one here. Let's put one here. Let's put one here and here. I'm gonna put one there too. Why not, right? When in doubt, at a breakpoint. Okay. So let's run this with the debugger and kind of actually visualize what's happening here. Okay, so we got our grid size, we have our grid, we have our, our first position now has a 1 on it because we have visited it. And we have our queue, which is now going to be initialized with that first coordinate. So there's a length of the queue, great. So we pop off, there's our current, that's our first node that we're visiting. So our current X is 0, our current Y is 0, right? So is there a neighbor under it? There is a neighbor under it, right? So our under neighbor Y is now going to be 1. And let's see. Yeah, our under neighbor Y is 1. Our current X is 0 still. And it is less than our grid size. So it's not in the queue, right? Because now we have under neighbor Y and current X, which is 1, 0, which is not in the queue. So it's going to put it in the queue. And then it's going to, right, we are going to take whatever is paths at under neighbor Y at current X, right? So is it going to show me what that is? All right, no. So paths at under neighbor Y, which is 1, right? So that is right here. And then current X, which is 0. So that's this first 0 in the second row. And we are going to add to it 1, right? Because so far there's been one path that has led to this node, and there's only been one path that has led to this node. So let's watch that, right? So now we have a 1 here as well. And now, breadth first search, we're going to look at its right neighbor before we continue down into that branch. So we have our right neighbor X, which is now going to be 1. And we're going to, so now we have, I think, 0, 1, right? Yeah, 0, 0, 1, which is not in the queue, right? So let's see what's in the queue. Now 1, 0 is in the queue, which is this one right here. So it's not in the queue. And we are going to add to it now the paths at the current Y, which is this one right here, right? And then the right neighbor X, which is going to be this one. So it's going to be the first row, second column. And we are going to add to it 1, right? So now there's going to be a 1 and a 1 and a 1, because for each of these paths, there's only been one path that has gone to those nodes so far, if that makes sense. Okay, so here's our new paths, right? Okay, so there's stuff in the queue, which is the first node's right neighbor and the first node's under neighbor. So we're going to pull off the under neighbor first. So this is going to be 1, 0. So that's going to be this one, right? Because again, it's a queue. So we're going in order here. So let's continue. So under that is going to be 2, right? So that's going to be this one. So let's watch that happen, right? So it's still in the bounds. It's not in the queue yet. So we're going to add it to the queue, and then we're going to add to it, right? So now this one is also going to have a 1. So wait, where are we? So this is, so right now we are at 1, 0. So this one, right? So we are going to add to it. We are going to make its next neighbor, which is going to be this one, have whatever this one had, right? So now that's going to be 1 as well. And again, we've only ever done one path towards that node so far, which is why we're just doing 1s at this point. And you'll see what happens when we finally get to an overlapping path. But okay, so let's continue to step through. So there we have another 1, right? So now we're going to check its right neighbor. And its right neighbor, I think, is going to be, let's see, so 0, 1 is, I think, so its right neighbor is going to be this one, right? So that's, no, its right neighbor is going to be, where are we? So the current Y is 1, right? So we're here, right? And the current x is 0, right? So it's now we're at its right neighbor, so we're talking about this one, right? And that one is now also going to get a 1 because we've come to it from something that's just has a 1. So let's watch that happen. So now we have a 1 there as well, right? Okay, so now we are back to our queue. We're at 0, 1. So that is going to be, right? So 0, 1 is this one right here. And I think we're going to probably go to the right, maybe, right? So there oh no, we're going under it. Oh, so under it already has 1, right? So what's going to happen now? So we've already gotten to its under neighbor through the other path, right? We've seen that neighbor already from a different path. So we're seeing it again, and that's fine, but we want to track that. And now we've gotten there 2 different ways. So that's a second path, right? So let's see what happens here. So the under neighbor and the current x, right? The under neighbor is 1 and the current x is 1. So that's 1, 1. 1, 1 is in the queue, right? It's already planned. We were already planned to see that. So we don't have to add it again. But we do want to track that we've seen it twice now. So that's why this addition is not in this, it's not indented to be under this if condition to check whether it's in the queue or not, because that's the whole point. It is in the queue from something else. So we want to track that and add the, appropriate number to it. And so this is going to now become 2 because we've gotten to this node 2 different ways. So now we have a 2 there. And that's kind of how that works. It's a little tricky. It's hard to wrap your head around, I would say. But essentially, I guess we can walk through this whole thing, but I think that's going to take a while. I highly suggest that you guys go through this and kind of really just like walk through it and, play with it a little bit, because I think that it's a bunch of confusing concepts, and they're kind of layered here. It's graph traversals, it's dynamic programming, it's kind of keeping track of a grid and knowing the positions of where you are at any given point while you're traversing. So I think the most important thing here is to just really, really understand it, and to not just kind of write it and like, it works. Really understand it, because like the computer is not like, it's ones and zeros, right? Like it does work. It doesn't like just kind of work, sometimes, sort of, I don't get it, maybe. So I think it's really important to take the time to kind of step through it and understand why it works, and kind of be able to almost take these different concepts and plug them in any sort of interview problem. So yeah, that's my advice for this sort of thing. And if you guys want more programming, like in-depth dynamic programming, like slides and stuff, we can definitely do that for you. So leave it in the comments below. All right, we've made it to the end. This was a very dense back to basics video, I think. So I hope it was useful, helpful. Again, do this yourself. Really, really, really go through it and kind of walk through the program with the computer. And I think that's sometimes the only way to really understand these concepts and like really get it in your bones. You know what I'm saying? If you like this kind of content and you want more, I know we've done videos in the past all about dynamic programming and recursion, but we can certainly do more kind of slides style, lesson sort of stuff, content relating to these difficult concepts. And keep up the good work. This stuff is not easy. So remember that if you are grasping this, that's awesome. Pat yourself on the back. If you are not grasping this, that's totally normal. It's really weird concepts, all of these things, in my humble opinion, at least. So keep up the good work, keep practicing. Again, I think it's all about like understanding the patterns behind these interview problems and seeing that even though there are an infinite number of problems out there, there are a finite number of actual like topics and like, little pieces to all of these problems. And if you really understand those well, you can kind of plug all of the different concepts together and solve any algorithm. So enjoy, have a great week, everybody, and I will see you in the next one.